here's how today is going to play out. So we're kind of in this transition between linear momentum and then angular momentum, which we will start at tomorrow. So to kind of tie in a whole bunch of different things, I've given you this problem on this piece of paper. We are going to work through it together. Make sure that you understand all the subtleties of this problem. Because I promise you, the test, which is week today, you are going to have a problem like this. The only thing I can do is change the values. I'm going to keep the exact same parameters, how it's defined, how everything works. So we're going to work through this, make sure everybody knows exactly how this is done. Once we get done with that, I've got a video that kind of shows how change in momentum works out with car crashes, and you don't have any homework tonight. So, okay. Okay, so here's the story, my fine fellow physics students. We're going to drop a ball from a height of 1.85 meters. It's going to hit the ground, bounce back up to a height of 1 meter, okay? And you've got the mass of the ball, which is 254 grams, and you're told that it's in contact with the earth for a certain amount of time. So, and then you need to do a whole bunch of things. You need to find the initial velocity of the ball, the final velocity of the ball, the change in momentum of the ball, velocity, time graph, forces, all this stuff. So, on the test, literally, the only thing I can do on this problem is change the numbers. So, if you look at this situation, here's kind of the setup. Here's about 1.85 meters. I drop it, boom, it's going to hit the ground. It's going to bounce back up to a height of 1 meter. Okay, so what we're looking at is the analysis from here to here, and we want to specifically find the change in momentum when it's in contact with the ground. Okay, so that's what we're after. The ultimate goal is to find the change in momentum when it's in contact with the ground. Now, I tell you on this problem, and I'm going to keep the same parameters on the test question. Anything down is going to be a negative value, okay? Whether that's force, acceleration, displacement, doesn't make any difference. Anything going down is going to be a negative value. And I'm not going to be a jerk, okay? On the test, I'm not going to go, oh, I'm going to mess with them. I'm going to define down as being positive, okay? No, down is still going to be negative on the test. But one of the things that's going to be very critical, and I'm going to show you this as we go through this, is that you maintain that system where down is negative and up is positive. So, let's start kind of at the end and work our way forward. So let's start with the velocity time graph. So, scooter, ball is here. I'm going to drop it. So where's my velocity time graph going to start?
0.
0. Then what's it going to do? Slope up or slope down?
Slope up.
Scooter, which direction does it fall?
Oh, sorry, slope down. Sorry, negative down.
Negative. Okay. So, Scooter, maybe something like this.
Wait, yes.
Deacon, what's the slope of that line going to be? Negative what? Negative. What?
9.8 meters squared.
Why?
Because of the acceleration.
That's the acceleration caused by gravity.
I said that.
You said meters squared, buddy.
No, I
Get
didn't.
on my leg.
I got you.
Yeah.
I knew you. Okay. So, why is the slope negative 9.8 meters per second squared?
I don't know. Why is it?
What's the only force acting on it?
Gravity.
Okay? So this is going to be important. This is going to be when it hits the ground. Okay? So when it hits the ground, what's the sign of the velocity going to be? Do not make this difficult. Negative, which direction is it going? Down? Okay? So this is gonna be some negative velocity when it hits the ground. True? It's gonna be some negative velocity. Cool. Now, at that point, it hits the ground. What's that graph gonna do as soon as it hits the ground? Connor S.
It's gonna go up.
Same slope or steeper slope?
I'd say something. Steeper.
You say something.
Something steeper.
Why?
Um,
How long is it in contact with the ground? Long time, short amount of time?
short time.
Short amount of time,
Yeah.
okay?
Wait. Yeah. Yes.
Okay, so maybe something like this. So, what's the sign of my acceleration
Oh
gonna
yeah, I'm
be?
dumb. Yeah.
I'm done,
I
yeah.
wasn't thinking straight for a second. Okay.
Are we thinking straight
Yeah,
now?
We are.
Let me check that theory. What's the sign of that acceleration gonna be?
Positive.
Why?
Because it is going against the original velocity.
Kinda. Is it slowing down when it hits the ground?
Yes.
Do you have negative velocity?
Yes. So there. Yeah.
So I've gotta have
Yeah.
some positive acceleration, true?
Yeah.
Okay, so it comes in, it hits the ground. At this point, the ball has stopped because the velocity is 0. Okay, so we fell, we hit the ground, the ball has momentarily stopped. Now, Luke Etheridge, what's this line going to do? This is when it has stopped at the bottom. Now, what's that line going to do as it bounces up? You have 3 options. It could slope back down like this. It could become a more shallow slope like that, or the exact same slope.
Won't it slope back down?
Why?
Because it bounces and then it's up at the top again at 0, and then gravity's gonna pull it back down. It's not gonna stop and it's not gonna bounce and then stop in the air and then shoot up again.
But riddle me this. When it bounces off the floor, which direction is it going?
Up.
So the velocity vector is pointing up, right?
Am I reading the graph wrong? Doesn't it hit down there?
Yeah, it hits at this point. So this is when the ball is being slowed down.
Oh, it's still in contact. Oh, no, it's gonna go up then.
Yes.
Oh, sorry.
Same slope?
Yeah.
Same slope. Okay? Now, at this point, it's going to leave the ground, right? It's going to leave the ground. So here's my question, and this is like an absolute value thing. When it leaves and bounces up, and again, this is just an absolute value, do not give me your nerdy math answers, okay? This is not a math class, this is a physics class. Is the velocity when it leaves bigger or smaller than the velocity that it has when it hits? Why smaller?
It's not gonna go up as high as it where it started.
Because if it left with the same velocity that it hit with, how high would it go up?
Back to the same place.
It'd go back up to 1.85 meters, which would be cool to see, because I could drop this golf ball and I could walk away and it would keep bouncing back to the same height every time. It just keep bouncing back, bouncing back, bouncing back. And I could just walk away and it's like keep lecturing and the ball would just keep bouncing. It's like you all would lose all track of time, but that's what it would do, right? So when this leaves the ground, so imagine you can watch this in slow motion. It's going to hit the ground. It's going to slow down very quickly. You're going to store energy in the compression of the golf ball. Then it's going to bounce off. But as soon as it leaves the ground, Thatcher, what's the slope of that line going to be? Or what's that line gonna do as soon as it leaves the ground?
Oh, start going up.
No, after this point right here, this is when it leaves the ground.
When it
So-
leaves the- Oh, start going back from
And what would the slope of that line be?
negative 9.8,
Why?
because gravity's only force acting on it.
Gravity's only force acting on it. So this line is also gonna be negative 9.8 meters per second squared. Okay? So this transition is gonna happen really quickly. It isn't like I catch it, stop it, and then throw it back up. Okay, it's like bam, very short amount of time. So this is gonna have a positive acceleration to make it slow down with negative velocity. Is this still gonna be positive acceleration? Sydney,
Yes.
why?
Because it's speeding up and the velocity is positive. So
Beautiful. Okay? Because now I have positive acceleration with positive velocity, therefore I have to speed up. So here's my question. What are the times when that ball was speeding up?
When it's going down.
When it's going down, and there's another time.
When it's making contact with the ground.
You gotta be more specific. Because there's a whole bunch of things happening without things making contact with the ground. Dylan?
When it bounces.
Yeah, so in this portion here, that's when that golf ball is like decompressing and it's bouncing off. So it's speeding up here because you have negative velocity here and you have negative acceleration. Here you have negative velocity with positive acceleration, so you are, slow it down. Here you have positive acceleration with positive velocity, so you are speeding up. And then I've got negative acceleration with positive velocity, and I am slowing down. Okay? Connor A, is the momentum of that ball as it goes through this, is the momentum ever constant?
No,
No. Why not?
there's some acceleration.
Yeah, throughout the entire time. I have no constant velocity. The momentum of this golf ball is continuously changing throughout the entire time. I have no constant velocity, therefore my momentum is always changing. Cool. Okay. Now, let's talk. So what I want to find is the velocity at impact with the ground. So I know the initial velocity is 0. I know how far it falls is 1.85 meters. I know my acceleration is negative 9.8 meters per second squared. And I'm in search of the final velocity. So Connor M, what equation relates velocities and distances but does not involve time?
That equation.
That equation. Well said, Grasshopper. So I got v squared equals v naught squared plus 2ax. Am I after v or am I after v naught? Adrian?
V.
Yeah, I'm after my final velocity because I know my initial velocity is
0.
0. So I got v equals the square root of v naught squared plus 2ax. So what I'm going to do is wrong. Okay? Do not do what I'm about to do. And that's not the part that's wrong. 2 times negative 9.8 meters per second squared times 1.85.
Oh.
I said it was wrong. Why is this wrong?
Don't forget to have your negative displacement.
Yeah, so if I have this, and one of the things I'm going to look at on this problem is the detail, the little nuts and bolts of this problem. If you have this, I'm snarkily going to write, wow, imaginary velocity. But can we just randomly make this negative? Well, here's the story. You're gonna make the ground the reference point. That's 0. My initial position then is gonna be what? 1.85. My final position is going to be Deacon. How do you calculate displacement knowing positions?
Position final minus position.
So my final position is 0, my initial position is,
1.5.
so this becomes negative 1.85. I am going to look for that detail when you work this problem, okay? I am going to look for, hey, do you understand how this problem works? So, Andrew, work the magic with the calculator, let me know what you get.
Negative 6.02.
Now, your calculator will lie to you when you do this. Because when you do this, your calculator is just going to give you 6.02. Okay? That's what your calculator is going to tell you. But, Chloe, what's the square root of 4?
2.
Or?
Negative 2.
So what do you have to do because you're taking the square root of it? You just have to choose the negative root. Okay? So you got to choose, go, oh, I need to make that negative 6.02. So, here's another reason why that displacement is a negative 1.85. Because if you go back up to this velocity time graph, and you find this area, which is going to be the displacement, so that would be some negative velocity multiplied by some value of time. There's another way that reinforces this idea that, oh, this has to be a negative displacement. Cool. Now, so at this point, I know that's negative 6.02 meters per second. So, when it leaves here, Sydney, what do you know about the sign of the velocity when it leaves the floor? Positive or negative?
Positive.
Okay, why?
It's going away from the floor.
Going away from the floor. So I know this has to be a positive velocity. This is negative 6.02. Is that velocity there going to be bigger or smaller than 6.02?
Smaller,
Why?
because it's not gonna reach the same velocity.
Think scooter. It's not going to reach the same height. Okay? Because it's only going to go up to 1 meter. So we started at Sydney, we're going to bounce up to Scooter. Okay? So it makes sense. So this area here is going to be Scooter. And this area here is going to be Sydney. Okay? Because you're going to start at 1.85, but it's only going to bounce back up to 1. Well, you have such a visual on this now, don't you? You absolutely do. Okay? All right. Now, on the way up, am I searching for V naught or am I searching for V? V naught or not to V naught? That is the question. Connor S. To V naught or not to V naught?
That was not what
I
we
don't think that would change the math that much. I don't think it would change the math that much, but yeah.
Oh, it is V naught, yeah.
It is to V naught. Because what's the final velocity?
0 because that's
0. You have to figure out how fast the ball has to be going to bounce up to a height of 1 meter. So, we're going to start with the Connor M equation that says V squared equals V naught squared plus 2AX. So, I need that solved for V naught. So that's going to be V squared minus 2AX, and the square root of that is going to equal V naught. Now, this is where you have to pay attention to what you have. On the way up, what's your final velocity gonna be? 0. So I have 0 squared minus 2 times negative, I'm running out of room, negative 9.8. Now, do I make this displacement negative 1? Andrew?
Because you have the negative 2.
Well, beyond that, which direction is the ball going? Up. What's the final position?
1.
What's the initial position?
0.
So therefore, the displacement is positive 1. On your velocity time graph, if you go back up to your velocity time graph, in this portion of it up here, right? On this portion, that's above the horizontal axis, so that's going to have a positive displacement. Oh, that's also going to be 1 meter, okay? So Sydney's going to have a negative displacement, Scooter's going to have a positive displacement, okay? Cool. Now, again, this is what I'm going to look for. Did you... Oh, I hate this thing today. I literally just... Okay, pretend that that's not there. So, what I'm going to look for is that does this work? So I've got 0 minus a negative number multiplied by a positive value. So I end up with positives underneath the radical. Life is good. So Andrew, what do I get out of this?
4.43.
What'd you get?
4.43.
4 point.
Apparently,
43 meters per second.
Should put in your calculator faster.
Now, does that match with what we said? Okay, only AP Physics students would have a contest, but should have put it in your calculator faster. Okay? It isn't like, oh, I can throw a fastball faster than you can. No, I can put numbers into a calculator faster. Oh, I love teaching you guys. Okay, so does this match with what we said was going to happen? Is it less than 6.02?
Yes.
Is it a positive value? Yes. Cool. So, I've got the 4.43 meters per second. At this point, do I have enough information to calculate the change in momentum when the ball is in contact with the ground?
I think so.
You know the mass of the ball. You know how fast it's going when it hits. You know how fast it's going when it leaves. By math, you can calculate change in momentum. True? Oh! Crazy. Crazy talk.
Crazy. Shut us crazy ones.
Tyler, shut your mouth.
What? You guys just stop.
Guys, calm down.
Okay, so change in momentum is mass times V minus V naught. Now, this is the trickiest part of this problem that I'm about to go through right now. Okay? So, here's this interaction with the ground. It comes in at negative 6.02 meters per second, but it leaves at 4.43 meters per second. True? Okay? So, here's my question. When it's in contact with the ground, which one of those two is my V naught? The negative 6.02 or the 4.43? Andrew.
Negative 6.02.
This is my V naught. Now, this is where this gets a little bit weird. So, when we found that value, we found it as V, because we figured out how fast it was going when it hit the ground. But the V here becomes the V naught when you're looking at the change in momentum part. Okay? Now, you found 4.43. That was the V naught when we found it, but in terms of the change in momentum, that is actually the velocity. Okay? So that's the little wrinkle in the space-time continuum. That V becomes V naught becomes V. So, at this point, we know the change in momentum is going to be the mass, which is going to be 0.254 kilograms. And then my V is going to be that 4.43 meters per second minus my V naught. And again, you have to be careful because that's going to be minus a negative 6.02. Yes?
I have an answer.
What is the answer?
2.66 Newton seconds.
3 point what?
2.66 Newton seconds.
2.66 Newton seconds.
And Tyler, where you at?
Universal.
Now, that's the change in momentum of the ball. What's the change in momentum of the Earth?
About that much.
Same.
The exact same, but it's going to be a
Negative.
negative value. Oh, okay. So when I bounce that thing, the change in momentum of the Earth is going to be negative 2.66 Newton seconds. Cool. Got that. Now, I told you that the ball is in contact with the ground for 1.28 times 10 to the minus 2 seconds. Someone who has a lot of free time did the math, like if you play 18 holes of golf, the total amount of time that the club it faces in contact with the ball is actually like less than a second because it's just bam, okay? So this isn't very much time. So at this point, knowing the time, could you calculate the force acting on the ball?
Yes.
Yes. Why? Force times time equals change in momentum. So you know force times time equals change in momentum. True? Now, before you do any calculations at all, is the sign of the force acting on the ball going to be a positive or negative value? Why? Okay, I'm going to have a positive acceleration, but physically, when the ball hits the ground, which direction is the force acting provided by the Earth? Up. I can't end up with a negative force. Because if I end up with a negative force, then you're going to tell me that, oh, I'm going to make the ball bounce up in the air, but I'm going to apply a downward force to it. Okay? Which makes no sense. All right? It makes no sense at all. So that's why I know in terms of the ball, the force has to be a positive number. Cool. So, somebody take that
207 newtons.
change in momentum, which was 2.66,
Yes.
and divided by that time of whatever that is,
1.2 to the negative second.
times 10 to the minus second. The seconds cancel out, and what do you get?
207.
So call it 207 newtons. Okay? Cool. Now, can we calculate the force that the ball exerts on the Earth?
Sure.
Do you know the change in momentum of the Earth?
Yes.
Is the time going to be the same?
Yes.
Yes. So I'm going to take negative 2.66 Newton seconds and divide that by 1.28 times 10 to the minus 2 seconds. And a miracle of miracles, I'm going to get, which verifies Newton's third law of motion. Because for every force there is opposite force, right? So the ball can't push on the Earth more than the Earth pushes on the ball. Congratulations, we just verified Newton's third law. At this point, Thatcher,
Yeah.
could I determine the acceleration of the ball while it's in contact with the Earth?
Yeah.
By doing what?
F equals in there,
You know the force acting on the ball.
yeah. Can you say it?
Yep. So what are you gonna do?
What am I gonna do?
Yeah.
By the force by the mass?
Yeah. So I'm gonna take 207 newtons
Good man.
and divide it by 0.254 kilograms. And you're gonna get like 800 and some.
815.
What?
815.
815 meters per second squared. Now, Thatcher, since you took this and ran with it, how does that 815 relate to that graph?
That's the force exerted over the time it's on the ground.
Otherwise known as,
Force mass.
you're making this difficult.
Oh, brother. How is the slope, the velocity, time graph,
What does the slope of a velocity time graph give you?
acceleration?
Did we just find the acceleration?
Oh, yeah. Yes. The
Yes.
slope of the line,
Ah, it's the slope of the line. Where?
when it's bouncing.
Yes, from the time that it hits until it leaves. So that 815 meters per second squared is the slope of that line, which is going to be really, really steep because it doesn't take very much time. Okay? Now I know the slope of the line. Cool, got it. Okay. Now, I have one thing left to do, and then we're done. I need to find the acceleration of the Earth. Is the acceleration of the Earth going to be negative 815 meters per second squared?
Definitely not.
Hopefully not. That would be bad. Why?
Because that, well, things would happen.
Things would happen.
We slingshot it out of the solar system.
Yeah, I mean, think about a Friday night in basketball season. You know, all across the United States, kids are bouncing the ball, right? If the acceleration was also equal and opposite, every time a kid bounced the ball, bam! Okay?
It'd be fun though.
The Earth would accelerate out from underneath it. Why doesn't the Earth accelerate out from underneath us with any noticeable value?
Because
The
it
mass of
would
the Earth is really big. It has a lot of inertia. It has a lot of stuff inside of it. By the way, if you ever go to college and someone says, "You take physics, yeah, what'd you learn?" Mass is stuff. It's like, okay, so Thatcher,
Yeah,
how can I find the acceleration of the Earth?
5.979 times 10 to the 24.
How the?
So I'm going to take negative 207 and divide it by the mass of the Earth, 5.979 times 10 to the 24th kilograms.
Do you want an answer?
I do.
3.46 e to the negative 23rd meters per second.
Times 10 to the negative 23rd meters per second squared. So here's what I want you to get out of this. Okay?
Everybody jump all at once.
Anytime you have a collision, what do you know about the changes in momentum? Equal and
Opposite.
what about the forces?
Equal and opposite.
Are the accelerations equal and opposite?
No.
What's the only way the accelerations can be equal and opposite?
Mass.
The two masses were the same. So if I could drop a 5.979 times 10 to the 24th golf ball, hey,
We don't die.
that would be really weird. Okay, so again, I promise you, the test a week from today, you're gonna have a problem like this. What's the only thing, I have 4 things that I can change. The initial height, the height that it bounces to, the time that it's in contact with the ground, and the mass of the ball. That's it. Those are the only things that I can change, okay? So if you wanna practice this, take this, mark out the numbers, make it 2 meters and 1.5 meters, and change the time, change the mass, okay? You just have to understand the process. But what I'm gonna be ultimately very, very nitpicky about is the process. Do you have the correct negative signs? Are you finding V? Are you finding V naught? Do you have the correct sign of the velocity when it hits? Do you have the correct sign of the velocity when it leaves? That's where the devil is going to be in the details, okay? Pay attention to those little things. So you know exactly what one of the problems is gonna be. The only thing I can do is change the numbers. Okay, so the video that you're gonna watch, it was made probably, I don't know, probably 15 years ago. But the purpose of the video isn't to show you where we are now in terms of safety with cars. The purpose of the video is to show you where we were with safety of cars. So you all grew up with like seat belts and child restraint seats and airbags and all this. You grew up in the post-modern era of safety in cars, okay? If you go back and look, you asked for up until like the 1950s, 1960s, if you wanted seat belts in your car, you had to special order it with seat belts. Okay? They were not standard issue. That was something that you had to request because they said, you'll be okay. Don't worry about it. Okay? Cars are big, you're gonna be fine. So, and again, as you watch this video, view this through the prism of one equation. That force times time equals change in momentum. Okay? So let me switch over to that computer and we'll make this happen.